Well, welcome everybody. This is Mr. B, and we're going to continue our study of the universe as we move into this third Wicks, evidence of the Big Bang Theory. And we're going to be looking at the side. Most of today, we'll be looking at the side with of your Wicks with all the blanks. This looks a little different than your normal Wicks. We're going to be filling in some blanks. And then we'll do a little bit on the back side. If you turn the page, we'll do a little bit on this side. But the majority of this back side will be filled out in class. Now today we are talking about evidence of the Big Bang Theory, and when we had our origins of the universe discussion, Ms. Timmons talked about how there were several evidences of the Big Bang, but probably the biggest and most important evidence of all is that the universe is expanding, and not only is it expanding, but it's expanding at high rates of speed. And you know, I've had a lot of students ask me, how do you know? How do you know that the universe is expanding? How do you know that galaxies are moving at incredible speeds? How do you know these types of things? And honestly, most of what we know about the universe is because of light, or what's referred to as the electromagnetic spectrum. And so today we're going to delve into light a little bit and see if we can increase our understanding of the evidence of the Big Bang Theory. Now, the number one evidence of the Big Bang Theory, the number one piece of evidence of the Big Bang Theory, and you want to fill in these blanks, so this is number one on your Wicks there, is called redshift, blue shift. So you want to fill in those blanks, redshift, blue shift. And then number two, redshift, blue shift, is evidence that the universe is expanding. And you can see I've underlined this in the purple here. But redshift, blue shift is evidence that the universe is in fact expanding. Now, if we're going to understand how redshift and blue shift work and how light shows us things about the universe, we're going to need to understand a little bit about the electromagnetic spectrum. Now, that is the third blank. We have to have some understanding of the electromagnetic spectrum. And don't let that big word scare you. All the electromagnetic spectrum is light. Light that you can see and light that you can't see. And we're going to take a look at how it has revealed things to us about our universe, like the fact that it's expanding. So in order to understand a little bit more about the electromagnetic spectrum, I have a short video I want you to watch.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
All right, so again, just a short little video to introduce the electromagnetic spectrum. I want to jump in there in a little more detail. So I want you to turn your wicks over to the back side of the page, and you'll notice at the top of the page there's a diagram that looks like this, very similar to the diagram at the top of your page. And let's jump in there and kind of talk about some of the characteristics of the different parts of the spectrum. We're going to go ahead and label the different types of waves, the first three, and you're going to label these in the boxes, the top boxes on your wicks. The first three are radio, microwave, and infrared. You can go ahead and label those. Some things that you'll notice about radio waves: you'll notice that the wavelength, that's the distance between 2 points on a wave. We'll talk about maybe the top of the wave here. You have the top of the wave to the top of the wave, and you'll notice that radio waves have a very long wavelength. And the video said they could be up to a football field. Here on your diagram, it's talking about how they might be the size of a building. Radio waves are used for a lot of things: walkie-talkies, your radio in your car. So they're very common, radio waves. And the thing about radio waves is you can't see them. This is light. Most of the light spectrum you cannot see. Then you have microwave. Microwaves are just like what they sound. It's the waves used in your microwave to cook food. You also use them, and you may not know this, it's the waves that provide signal in your cell phone. Now these wavelengths begin to get a little shorter. In fact, a lot shorter. Where a radio wave could be the length of a football field, microwaves would probably be more like a grain of sand or a grain of sugar, as it says there on the screen. And again, you can't see a microwave. And then you have infrared. Infrared is invisible light. Again, you can't see it, but it's used to see temperature. Infrared would be the heat given off from a fire. It would be the heat given off your body. That's why when, like, the military uses night goggles, what it's looking for is those night goggles can see things that have a temperature because it reads infrared light. You can't see it with your eyes, but special equipment can pick it up. These wavelengths are shorter than a microwave wavelength, but still longer than many of the types of lights on the spectrum. So you have radio waves, again, used in walkie-talkies or radio in your car. Can't see it. You have microwaves, smaller wave like the grain of sand, used in your cell phones. You have infrared that gives off heat, or infrared is the heat given off like from a fire or your body, even smaller still. Then you have the only portion of the light spectrum that can be seen. It's the visible light, and this is the colors you see around you. Roy G. Biv is the acronym. Red, as you go across the spectrum, you have red. Orange is the O. Yellow, green is the G. Blue, indigo, and violet. That's why they say Roy G. Biv is the acronym. ROYGBIV, red, orange, yellow, blue, red, orange, yellow, green, blue, indigo, and violet. So that's the visible light spectrum. And then you have, continuing on with more invisible light, you have the smaller wavelengths on the right-hand side of the spectrum here. You have ultraviolet. That's the light that comes from the sun. It's very small. It would be, those waves would be as small as, like, say, an H2O or a water molecule. These are more harmful to humans. Shorter wavelength means it has higher frequency, which means it has higher energy, and so ultraviolet lights can actually damage your skin. You have X-rays. Overexposure to X-rays, even like the ones you get at the hospital when you break a bone, can be damaged. That's why X-ray technicians will stand behind a wall, a lead wall, in order to protect themselves from overexposure to X-rays. These have shorter wavelengths than ultraviolet. They'll be about the size of an atom. So very small wavelengths, very small waves, and higher frequency can be harmful to humans. And then you have the smallest waves of all, the gamma rays, and they are about the size of the nucleus of an atom. And these are your radioactive rays. These would be, or radioactive waves. These would be waves that are generated at a nuclear power plant or a nuclear bomb, and can be very damaging to humans. And so these are the different waves that are on the electromagnetic spectrum. Again, you can't see the first three, radio, microwave, or infrared. You can't see UV X-rays, or gamma rays. The only light you can see is here in the middle. And again, the ones on the right, ultraviolet, X-ray, gamma, are more harmful to humans. I think there's a place for you to write that information down on the front side of your wicks. You'll notice number 4 asks you to list 3 types of light radiations that can't be seen, and really there are 6 that can't be seen. All of the radio, microwave, infrared are invisible. Ultraviolet, X-ray, gamma rays are also invisible, but you only need to record 3 of them in your wigs. And then it asks you to list 3 types of radiation that can be harmful to humans. That would be your ultraviolet or UV, X-ray, and gamma rays. And then it says how much of the number 6, how much of the light radiation can be seen. Of course, that would be just the visible light. So I'm going to stop here, pause for a moment. Why don't you write that information down in your wicks, and then we'll pick it back up with wavelength in a moment. All right, so we've been talking about wavelength and frequency on the electromagnetic spectrum. I think it would be important for us at this time to go ahead and define those. A wavelength, simply put, is the distance between 2 waves. If you look at the diagram below, if I just pick 2 points on the same place of a wave, let's say at the top here, if I picked this point and this point, the distance between those 2 points, the same place on the wave, would be the wavelength. Now, if you look at the electromagnetic spectrum, you'll notice radio wave has a much longer wavelength. The gamma rays have a much shorter wavelength. And this affects the frequency of a wave. Now, to define frequency, number 8, you would write how quickly a wave can pass 1 point in a second. Now, what does that mean? This is a still picture of a wave, but waves are not still, they're moving. And so let's say this wave were moving, and I pick this place right here where my mouse is to measure the frequency of a wave. Every time a wave passes this point, we would count how many times the wave passes that point in a second would determine its frequency. And so let's say the wave passes 10 times, this point 10 times in a second. But then another wave passes this point 20 times in a second. The one that passes the point 20 times would have a higher frequency, and consequently it would have higher energy. So your radio waves have longer wavelengths, they take longer to pass that point, they have a low frequency. Your gamma rays, which are much more harmful to humans, have a shorter wavelength, they pass that point much more frequently, so we say it has a high frequency, and because of the high frequency it has more energy and more harmful to humans. Alright, we've been talking about the wavelength and frequency of waves on the electromagnetic spectrum. I think at this point it would be important for us to write down a definition of those two things. So if you look at number 7, it wants you to define wavelength. And you would use the definition here, the distance between 2 waves. And what that means is if I were to pick 2 points on this wave, say the top of this wave and the top of this wave, and measure the distance between them, that would be the wavelength. Now the frequency would be, if I picked a point in space, say right here, and remember, waves aren't still. This is a still picture, but waves aren't still. They're moving constantly. And so if I picked a point here and counted how many times the wave passed that point in 1 second, that would be the frequency. If it only passed that point a few times, we might say it had a low frequency. If it passed that point a lot, many times, we would say it has a high frequency. So to compare waves, let me flip back, we might look at radio waves. Notice the wavelength from this wave to this wave, the wavelength from this point to this point is very long. And because that wavelength is really long, it's going to take a long time for it to pass a point every second. So we'd say it has a low frequency. Now look at gamma waves. Very short wavelength, and so it's going to pass that point every second much more frequently, and so we would say it has a high frequency. So the higher the frequency, the more energy, the more harmful to humans. The lower the frequency, the less energy and less harmful to humans. Now, I'm going to skip back here. I think it would be important for us to go ahead and label the two waves. On number 9, you want to go ahead and label, I'm sorry, you want to go ahead and label each of those. The one that has the more waves that are passing that point, we would say high frequency, and the one that has fewer, we'd label that low frequency. All right, so we're going to move into talking about red shift and blue shift in just a moment and how that's an evidence of the Big Bang. But before we can do that, we really have to understand a concept called the Doppler effect. And I have a short video I want you to watch on the Doppler effect, and then we'll come back and define some things.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense. But it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you. And a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch.
Okay, so that's the Doppler effect. And I want us to go ahead and write down a definition, a simple definition of the Doppler effect for number 11. And so just maybe pause the video and write this definition, that it's the wavelength and frequency change when the source of a wave is moving, like the car. When the car came towards you in the video, there was a high pitch, high frequency sound of the horn, and then when it passed you there was a low frequency sound of the horn. So you need to write that definition down. Now let's answer number 12 and 13 as well. What happens to the wavelength and frequency as an object moves close to you? Well, write this down for number 12. It's that the wavelength compresses as the object moves close to you. The wavelength gets shorter, the frequency gets higher, you hear that high pitch. Now number 13, what happens when an object moves away from you? The wavelength gets longer, it stretches it out, and the pitch or the frequency gets lower. So again, as the object moves towards you, shorter wavelength because it scrunches it up, and higher frequency, shorter wavelength. And as the object moves away from you, it stretches the waves out. You get lower frequency, longer wavelength, lower frequency. So you need to write that for 12 and 13. Now, turns out that the Doppler effect doesn't just affect sound. It also affects light. And it's where we get to the whole red shift and blue shift concept. So now, when an object is moving towards you, let's look at the, I'm going to pull these up here. Let's look at the bottom here. Because this is going to help you answer number 14. So when an object moves towards you, like this galaxy is moving towards the planet, the light, see the black line, it indicates the shift in light. Light shifts to the blue side of the spectrum. So this galaxy is moving towards the planet, the little black bar shifts towards the blue side. So you would say at number 14, what color of the visible spectrum do we see in a high frequency wave that's moving towards us because the light wave is scrunched up? We would say blue. Now, when an object moves away from us, when it's moving away, you would see, like this galaxy is moving away from us, the light wave is stretched out, longer wavelength, lower frequency, and you'll notice the bar here, the black strip, the black bar, it's moving more not towards the blue, but towards the red side of the spectrum. We call this redshift. Okay, so when an object moves away, we have a redshift because the wavelength gets stretched out and the frequency gets lower. When the object moves towards you, you get a blue shift because the wavelength gets shorter and the frequency gets higher. Now, how does that support? Why is that the major evidence to support the Big Bang Theory? Check out this video.
Hey there guys, this is Mr. Herbst here, and today our focus is going to be on what we call the redshift and blue shift. So to start with, the redshift and the blue shift is a phenomena that occurs with light. Over here we have our red light, and over here we have our blue light, and in between we have our Roy G. Biv. Now red light has a wavelength of about 7 nanometers, and blue light has a wavelength of about 4 nanometers. To fully understand the redshift and the blue shift, we must understand that different colors of light have different wavelengths. Thus, you ever heard of Roy G. Biv? This is where Roy G. Biv comes from. Our reds way up here have a very big wavelength, thus they go by less often. And our violets and blues down here go by very quickly, thus they have a higher frequency because they go by more often. So let's go ahead and consider that we have 2 stars. These stars are giving off a known wavelength of light. Now if one star, the one on the left, happens to be moving away from us, the light waves are going to be stretched out. Thus they are going to appear more red in color. The faster that star is moving away from us, the more red it is going to appear in color. Vice versa. If the star on the right, say, is moving towards us, it's going to appear more blue in color than it actually is. So with that said, there's something very interesting that occurs in our known universe. Almost all of the galaxies and all of the stars that we see in the universe are redshifted, which means all of them have a larger wavelength than what you would predict, which means that almost all of the stars and all of the galaxies are moving away from us. And what's even more interesting, that we find that the farther they are away from us, the more redshift that we see, which means they're moving away from us even faster. So what that explains is that as the universe is getting bigger, it's getting bigger at a faster rate. That's right, the universe is accelerating the rate at which it is expanding. Also, if we go ahead and reverse time, it almost appears that all of these galaxies and all these stars came from one central point. That's what we call the Big Bang. But that's another video. Anyway here guys, that concludes the redshift and blue shift. This is Mr. Herbst. I'm signing off folks. Y'all have a nice day.
All right, so hopefully that video helps you to answer number 15, explain how redshift is evidence that the universe is expanding. Again, just to sum it up, because galaxies, most of the galaxies in the universe are in redshift, meaning they're moving away from us, it supports the fact that the universe is expanding. And not just expanding, but expanding at high rates of speed. What would cause the universe to expand and expand at high rates of speed? Most scientists believe that it's the Big Bang Theory. Now, redshift and blue shift also help us to understand rotation in the universe. How do we know a galaxy rotates? How do we know a star rotates? Well, when you look at objects like a galaxy or a star, you will notice, if you're looking for redshift and blue shift, that one side of the star or galaxy is redshifting, meaning it's moving away from you. And then the other side of that star or galaxy is in blue shift, meaning it's moving towards you. So what would cause the same object to sometimes be moving away from you and sometimes be moving towards you, except that it is, in fact, if you look at my mouse, rotating. So that's how redshift and blue shift help us to know that stars and galaxies, for that matter, rotate. Okay, I'm going to wrap it up with a quick 1-minute video to help you see visually how redshift and blue shift help us to see galaxies and stars in rotation, and then we'll wrap this up for today. Thanks for listening, guys.
As a galaxy rotates, light from the parts approaching the observer are blue shifted, while light from the parts turning away from the observer are red shifted. By measuring these shifts, astronomers determine how galaxies rotate.